Hi there, folks. Welcome back. In this video, we are going to be working on simplifying radical expressions. And the reason why I wanted to make a video about this is because one of my students is doing this in his online class right now, and he's having a little bit of trouble. And I wanted to give him a full solution, but it is incredibly painful, incredibly tedious to type a solution using the text tool on Zoom. So I decided just to make a video of this instead of typing the solution. That way my student will be able to review this as many times as he needs to grasp the subject. So let's take a look at the official instructions we have today. So we have write an expression for each product that removes any perfect squares from the radicand. Assume all variables are positive. So let's talk about what that means real quick. So an expression we know is just anything that contains numbers and or variables. We know that the product is going to be an answer to a multiplication problem. And a perfect square can be a number or a variable. So let's review that real quick. So 64 is a perfect square. How do we know that? Well, if we take the square root of 64, we get a nice round whole number. So whenever we have these circumstances, whenever we take the square root of a number to get a whole number, the original number is considered to be a perfect square. So 65 would not be a perfect square because if we take the square root of 65, we get some decimal. And that criteria is what tells us that 65 is definitely not a perfect square. So a variable can also be a perfect square. So let's say we have x to the fourth power, and we want to take the square root of that. We get the following. Well, what we want to do first is rewrite the radical. So whenever you have something under a radical, it is equivalent to having whatever the thing is to the 1/2 power. So what we have on the right is equivalent to what we have on the left. We just rewrote it in a really different way, but the concept is the same. They both mean the same thing. So the reason why this is important is because we can get a better conceptual sense of what's really going on here when we take the square root of something. So we're going to use our properties of exponents knowledge here. So whenever we have an exponent on the inside like this, and then one on the outside like that, we always take the base, which is going to be x. We're going to raise it to the product of those two powers. 4 times 1/2 is 2. So that tells us that square root of x to the fourth power is equal to x squared. So that's what it means for a variable to be a perfect square. So what I want to do is I want to take this bit by bit. And a way to effectively simplify something like this, where there's one radical and a lot going on, we can give everything its own radical. We can give 8 its own radical, we can give x to the fourth its own radical, and then we can give z to the third power, z cubed, its own radical as well. So it's like being on the Oprah Winfrey Show. You get a radical, you get a radical, everyone gets a radical. So let's think about the best way to approach this. So the first thing we're going to have is square root of 8. We're going to give 8 its own radical. Let's figure out what the simplified form of square root of 8 is. So they want us to remove any perfect squares from the radicand. And by the way, a radicand is a fancy word for everything under a radical. So 8x to the fourth times z cubed, this would be our first radicand. And then our second radicand would be 50y to the second power times z to the fifth power. Those are the two radicands given to us in this problem. So they want us to remove any perfect squares. So we want to ask ourselves, does 8 have any perfect squares at all in its factors? So 8 only has 4 factors. We have 1, 2, 4, and 8. Out of those 4, only one of those 4 factors is a perfect square. That would be 4. So the process of removing a perfect square looks like this. So I'm going to break it up. I'm going to write it as 4 times 2. And then from there, 4 is going to get its own radical. 2 is going to get its own radical as well. So that's what they mean by this. So we removed a perfect square from the radicand. 4 is a perfect square. We just removed that. And then we can simplify this to be 2 times square root of 2. So this is considered to be the fully simplified form of square root of 8. So let's go ahead and write this. So we have 8y times, we just found out that this entire thing right here is 2 times square root of 2. So next we're going to give x to the fourth power its very own radical. And we know from the example I did a couple minutes ago that this is equivalent to x to the second power. X to the fourth, square root of x to the fourth is equal to x to the second. And then we have square root of z cubed. And then we're going to write everything else. We have 5x. And then we want to think about a way to rewrite this square root of 50. So the thing that comes to mind is to do something similar to what we did for 8. So 50 has quite a few factors. We want to think to ourselves if we can identify any that are perfect squares. Indeed, there is one. So 25 is a perfect square. So I'm going to take 50, square root of 50. I'm going to rewrite that as square root of the quantity 25 times 2. And then we're going to do something similar to what we did above. Square root of 25 is 5. 2 gets its own radical. So then this is the fully simplified radical form of square root of 50. So I'm going to replace square root of 50 with 5 times square root of 2. And then we have square root of y squared. So whenever we have a situation like this, whenever we're taking the square root of something to the second power, the radical and the exponent cancel each other out. So that means we're only going to have y. We're not going to have an exponent anymore. We're not going to have a radical for this particular part of the product. It's going to simply just be y. And then we have times z to the 5th under its very own radical. All right, so let's simplify things a little bit before we go further. So I want to multiply negative 8 times 2 times 5 times 5. So negative 8 times 5 is 40. Sorry, negative 40. Negative 40 times 2 is negative 80. We have negative 80 times 5, which is negative 400. I just multiplied all the constants together, and I got negative 400. So next thing we want to do is we want to simplify this z to the 3rd power and this z to the 5th power, see what we can do about those. But before we do that, let's see if we can combine any like terms together. Let's see if there's any opportunity to multiply similar things together. So we have a y right there, another y right there, an x cubed right there. No, sorry, x squared right there. And then this is an x. So let's go ahead and multiply the x's together. So we have x to the 2nd power times x. We get a total product of x to the 3rd. And then we will focus on the y's. So we have y right here, and then we have another y right there. Y times y is just going to be y squared. All right, fantastic. Now we just want to deal with the radicals. So we still have a square root of 2 we haven't done anything with. And then we still have another square root of 2 over here, I guess. So we have 2 of those square root of 2's right there. Square roots of 2, I guess, would be the right pronunciation for that. And then we have this square root of z cubed. Now this part's kind of tricky. You may not know what to do here. Let's see if we can break it up in a similar way to what we did with 50 and what we did with 8. So we want to ask ourselves, does this expression under the radical, does this monomial contain any perfect squares? And yes, indeed it does. So we're going to rewrite this as z to the 2nd power times z. And the reason why we want to do that is because z to the 2nd is a perfect square. The square root of z to the 2nd is just z. And then we're going to put the other z under its very own radical. So this whole thing just is equivalent to z times square root of z. So that's what this part is right here. This is just going to be z times square root of z. And then we're going to do something similar with x. We have x to the 5th power. And this one does contain a perfect square as well. So I'm going to write this as x to the 4th power times x. And then when we take the square root of x to the 4th, we get x squared. And then we have that times x under its very own radical. So this is equivalent to x to the 2nd power times square root of x. All right, so let's simplify things a little bit. So I see that we have 4 separate radicals, one right there, and then a 3rd, and then a 4th. So whenever we have a situation like this, under normal circumstances, we would put things under their very own radical. We'd put them under the same radical. We would have square root of 2 times z times x. But what we have is a little bit different than this. So what I want to do real quick is I want to multiply square root of 2 times square root of 2 together. We get a nice whole number. We don't have any radicals anymore at that point when we simplify. So this entire thing right here is equal to 2. So now that we have just a nice whole number to work with, I'm going to multiply this 2 by the negative 400 coefficient on the outside for a total product of negative 800. So this part right here goes away whenever we multiply to get our product of negative 800. We no longer have these square roots of 2 in the middle. So we're going to have negative 800 times x to the third power y squared. And now let's see what else we have. We have x squared times z. But actually, you know what? Now that we have more opportunities to simplify, we want to go ahead and do just that. We want to multiply this x by that x. So whenever we multiply things like this, we're going to add the exponents together. We get x to the 5th power. So I'm going to update this. Instead of it being x cubed, it's going to be x to the 5th. And then let's see what else we want to do. So we only have radicals left. But I forgot the z. We have just one single power of z. And then what we want to do next is we want to take the things we have left. We have a square root of z and a square root of x. We want to combine them and put them under the same exact radical. So this is going to turn into x times z under the same radical, square root of xz. So this right here is our final answer. We have effectively taken out all perfect squares from the radicand and simplified. All right, let's try another one. Next up, we have, this one seems a little messy. We have 2/3 times square root of 54a cubed times b to the 4th. (54a cubed, b to the 4th under the radical. And then we have that times 12, and then another radical containing 200b to the 6th power times c to the 7th power. So let's see if there are any opportunities to simplify this thing with just the numbers so far. So we have 2 constants to deal with. So let's combine these together. So 12 times 2 gets us 24. 24 divided by 3 is 8. So they're going to multiply together to get us a product of 8. Now we have the square root of 54. So let's think about an effective way to deal with this. So you might want to ask yourself, does 54 have any perfect square factors? Indeed it does. 54 can be written as 9 times 6. And then square root of 9 is 3. And then we have 3 square root of 6. The 6 doesn't have any perfect square factors, so that's why we just leave it like this. We can't do anything with it. So we're going to just simplify square root of 54 to be 3 times the square root of 6. And then we have the square root of a cubed. We want to do something similar to what we did in the last problem. We are going to break it up into the product of a and a squared. So square root of a squared is just a. So this is going to turn into just a times square root of a. And then we have b to the 4th power. So in this situation, we are going to have b to the 4th under the radical, which is another way of saying we have b to the 4th to the 1/2 power. 4 times 1/2 is 2, so this is going to turn into b squared. And then we have our other radical to work with now. So the number we have in this radical is 200. That's our constant. 200 does have a perfect square. I think it does have a few perfect square factors, actually. The most obvious one would be 100. So 200 is equal to 100 times 2 under the radical. So then we have square root of 100, which is 10. And then square root of 2, can't do anything with that. So now we're going to simplify square root of b to the 6th power. Well, half of 6 is 3. So square root of b to the 6th power is equivalent to b to the 3rd power, b cubed. And then we have c to the 7th under the radical. So let's go ahead and write this as c to the 6th power times c. Put everything under its own radical. So square root of c to the 6th power is going to be c to the 3rd power. And then we have a square root of c we can't do anything with. So this is going to be c to the 3rd times square root of c. And now we want to simplify wherever possible. So we have 8 times 3, which is 24, times 10, which is 240. And then we have square root of 6 times square root of 2 times square root of c. We're going to share a radical on that one along with the square root of a. We're going to put everything under the same radical. So we're going to have 6 times 2, which is 12. So we're going to have square root of 12. And the reason why I'm not putting this under the same radical is because I think we can simplify this a little bit further. I think we can take out a perfect square from square root of 12. So this is going to be under its own radical. And then we're going to put a and c under a separate radical. So we have square root of the quantity a times c, square root of this product. And then after that, the only things we haven't dealt with are the additional variables. So we have an a times b squared times b cubed. We're going to get b to the 5th for that. And then we have square root. We already dealt with that, but we do have a c cubed we haven't done anything with. So let's take a moment and simplify square root of 12. So 12 is the same thing as 4 times 3. I'm going to put the 4 under its own radical. I'm going to put the 3 under its own radical. Square root of 4 is 2, so we're going to have 2 times square root of 3. Which can be simplified to 480 times the square root of 3. So now we have a square root of 3. At this point, we want to combine the 3 and the AC. We want to put them under the same exact radical. So we're going to have the square root of the quantity 3 times a times c. And then everything else is going to be just as it appears. So we're going to have a times b to the 5th times c to the 3rd. And then we can't do anything else with this. We are completely done with this one. Let's do one more. So this next one we have is going to be 4 times the square root of 20 times 12 times the square root of 56. So in this case, ideally we want to maybe put 56 and 20 in terms of the same factors. It'll make it easier to do the arithmetic later on. But before we even talk about that, we're going to multiply the 4 times the 12. We get 48 as our new single coefficient. So I want to see if we can rewrite square root of 20 and see if we can take out any perfect squares. So 20 is the same as 4 times 5. Square root of 4 is 2. So we have 2 times square root of 5 as being equivalent to square root of 20. And then we have square root of 56. We want to think to ourselves, we want to consider why can't I talk today? We want to see if we can think of any perfect square factors of 56. So I think we might want to do something with 4. Because 8 times 7 is 56, which means 4 times 14 is also 56. Square root of 4 is 2. Square root of 14, can't do much with that at all. So what we have now is square root of 20, which is the same as 2 root 5, times square root of 56, which is the same as 2 root 14. So let's combine things together and then resimplify. So if we multiply 48 times 2 times 2, we get 192. If we multiply square root of 5 times square root of 14, well, 14 times 5 is 70. So we put 70 under its very own radical. And then we want to ask ourselves if 70 has any perfect square factors. Give me a quick second. So 70 does not have any perfect square factors. So this right here would be our fully simplified answer. All right, well, I hope this was helpful to my student, and I hope this was helpful to anybody who just happens to be watching this. If you're struggling with radicals, I hope I was able to clear things up a little bit for you. All right, guys, thanks for watching. See you in the next video.